Okay. So thank you all for being here. I know it must have been a really long week sitting in front of our computers, but hopefully this talk will be equally interesting and fun. Before I start talking about our work, I want to give you a little bit of background about me. So this is my first year of PhD, and this is my first time in PETS, which I'm very excited about. But before that, I used to be involved a little bit in privacy from an activist perspective. But as I am usually one of the few people who have a background in privacy and tech, I usually get asked the question by my activist friends, why don't we have an app that we can send messages anonymously? So I Googled the question, and it turns out you have to do a whole PhD for that. So I did, hoping that I'm going to find the ultimate answer to my question and the secret of building anonymous communication system. And as most PhD students know, in your first year of PhD, you will be reading a lot of papers. And in my field, I had to go back to 1981, basically the ancient history of anonymous communication, where Chom introduced the concept of mixnets. Basically, the idea, we will have a Chom mix that collects input messages and delay the messages, and hopefully the attacker is not going to be able to make a correlation between the output messages and the input. Between 1981 till today, there has been a lot of mixnet designs, such as Mixmaster, Mixminion, Vuvuzela, Loopix. All of these designs are great. However, none of them have been deployed at a large scale. So what's the problem? Well, the problem is these designs are very different. They use different design options, they have different parameters, and they even have sometimes different threat models. So to compare between, the comparison between these designs is often very hard, and we cannot use it, for example, with formal verification tools as ProVerif. There has been some theoretical work that resulted, for example, in the anonymity trilemma that put together these trade-offs between anonymity and bandwidth and latency. However, we still do not have a systematic approach of evaluating and designing mixnet-based systems. And the reason is mixnets are actually very complex. There is a lot of design options we have to choose from. We have different topologies, we have different routings, we have different mix types, and of course we should add dummy traffic, but then what's the tolerated bandwidth? When do we emit the dummy traffic? Should it be mix-based or client-based? And then there is other parameters, such as the number of users and the number of nodes. What if we design a system for 1 million of users, and then it turns out only 1,000 users will use it? Should we come up with a new design, or should we just adapt our system? And if we're going to adapt, how are we actually going to adapt the parameters? I wish there is such a book as Mixnet Design for Dummies, but there isn't. And this is why we need a platform that a simulator that will study the impact of different design choices on privacy properties, studies the impact of attacks, and takes into consideration these engineering trade-offs between the latency, capacity, and privacy. We can use this simulator to guide a development process of an ongoing project, and hopefully it will be a good open source tool for the research community. So hopefully now I motivated you. Now I'm going to tell you that we start working on this. The current version of the simulator we've been working on supports 1 million messages per second, and we tested up to 100 nodes. We use Python and SymPy, the discrete event simulator. The supported features of the current version of the simulator are the following topologies: cascade, free route, stratified. We also have the 3 types of mixes: pool, time, Poisson, and the 2 types of routing: source routing and hop by hop. So before I will show you the preliminary results, I just want to have a brief explanation for those who might not be familiar with the 2 different types of mixes we're using here. So the Poisson mix will delay each message according to Poisson process with a parameter lambda. And the pool mix will collect n number of messages, and each round will flush a certain percentage of these messages. For example, here we have 100 messages in, and each round the pool mix will flush 70 messages. If you like graphs and slides, then I'll have your back. I'm going to be showing a lot of graphs. And here we have a comparison between pool mix and Poisson mix. You can think like you're designing a mixnet-based system and you have everything figured out, but you're still confused between which type of mix you want to use. Should it be full mix or Poisson mix? Well, here, for example, we have an entropy-based anonymity according to number of messages. Well, when you have a small number of messages, clearly the pool mix will provide better anonymity. However, when you go higher in the number of messages per time unit, you have better anonymity provided by the Poisson mix. The entropy is constant in the pool mix, and that's due to the fact that the pool mix will always flush the exact same number of messages in each round. We can also test the latency between these two types of mixes. Here we have the latency is constant in the Poisson mix, and that's because the latency in the Poisson mix is set on the client side, so it's always constant. However, in the pool mix, we have very low latency when we have a higher number of messages. What we can also do with our simulator is test these trade-offs between the anonymity and the latency. For example, here we have two types of mixes, Poisson mix with two different delays. The orange one is the Poisson mix with a delay of 1/10, and the blue one is Poisson mix of an average delay per message is 1/100. You can see whenever, every time, no matter what the number of messages, every time you are willing to tolerate more latency, you get more anonymity, and that's the orange graph. We do kind of the same thing with latency and entropy, this trade-off in the pool mix. And here we have three pool mixes, one of 50 bandwidth, the second is of 100 bandwidth, and the third of 1,000 bandwidth. You can see that the latency is higher because here the pool mix will wait longer time to collect the 1,000 message. However, of course, it will provide better anonymity. Attacks. We like to talk about attacks. We like to talk about threat models. Here I'm going to show just one experiment about attacks. For this experiment, we use stratified topology, 9 nodes, 3 nodes per layer. And the first graph just shows as a baseline for what the entropy we get if we're using this configuration using 100,000 messages per time unit. The second graph is what if we have one corrupted node? We can see that the average is close to no corruption. However, we have a higher variance. What's interesting here is the third and fourth graph. Even though the capability of the attacker is the same, we can see that the third graph and the fourth graph, the attacker is controlling three mixes. However, if the 3 mixes are in one layer, we get much better anonymity. And this is because all the messages will go through only one corrupted mix. However, in the fourth one, some messages will go through an entire corrupted path. Another experiment we can use using our simulator is what is the impact of adding layers in a stratified topology. Intuitively, we can think adding layers will provide us better anonymity. However, what's the extent? Is having 8 layers better than 4, or should we stop at 3? We don't really know. So we can see here in the graph is adding 1 layer, 2 layers compared to 1 layer gives us much better anonymity. It's 2.5 bits, which means we have 5 times larger anonymity. However, the differences between 8 layers and 4 layers is really small. And keep in mind that the more layers you have, the more latency you will get. So maybe the trade-off should be between 3 and 4. 3 if you're thinking no layer will be corrupted. 4 if you're thinking, oh, there is a risk of one entire layer can be corrupted. As a future work, we have a lot of questions we want to answer. We want to study empirically using our simulator. One first thing is we want to compare previously existing designs, such as Mozilla, Mixminion, Lupix, maybe CMix. We want to test them on this simulator. A second thing we're thinking about is the impact of different traffic distribution on anonymity. Here, you can think of a scenario, you have a mixnet, and on top of it, you have 2 different types of application. One is messaging, and the second one is emails. Of course, the traffic distributions are going to be different, but should we have the same mixnet for 2 different applications? Will that leak information, maybe according to the traffic distribution, what kind of application you are using? Or the other scenario, maybe we should have 2 different mixnets per application. Another question we would like to answer is how can we design dummy traffic strategies based on different design options, different design decision. When we have a stratified topology, we have Poisson mix, should it be the same dummy traffic strategy of when we have, for example, like Vuvuzela, a cascade with time mix. Last but not least, what we think also very interesting is the directory authorities. Most of the papers about mixnet are assuming a centralized attack-resistant directory authorities, but none of these papers have explored the possibility of having decentralized directory authority. So maybe we can study that. That's all I have. Thank you for listening. Please, if you have questions or suggestions, feel free to email or here